Hey everybody, welcome. Before we get started into this lesson, some things that you may want to make sure you need right now before we get started is binder paper and pencil. You want to remember that each lesson's notes will be collected at the end of the spring break and will be worth a good chunk of your grade. The next thing you want is your full focus, so that means make sure that you're in a quiet space, that you have some earphones on, and that you're away from distractions, and that you have everything you need. Another thing is be prepared to learn. So make sure that when you're watching these videos, you have a learning mindset on, and that you're prepared to do some thinking. So keep that in mind, so that you could keep your brain active. Do what you need to make that happen, such as, having some coffee, whatever it is that you do. And lastly, have your resources at hand, whether that's your binder, if you brought it, any notes that you brought, or use the resources that I provided, specifically like the Chapter 7 Big Ideas packet. Either you have the hard copy of this, or you could go ahead and take a look because I've attached it on Google Classroom. This is basically listing off all the big ideas that we talked about in this unit. That's going to lead us into our artifact. And we're going to specifically be jumping into average rate of change, which is going to lead us into some more bigger ideas. So we're going to move past the basic average rate of change calculations, and we're going to be jumping into writing expressions of average rate of change. And it looks something like this. So you could feel free to look through it and feel free to look ahead for other learnings. We're going to be doing the lesson today in 7.2.3 called How Fast Am I Going? So for the quiz, right, it's going to be due at 11:59 p.m. today. So make sure that if you want to excel in the quiz, that you know the answers to these questions. Number 1, what is the secant line? Number 2, what is the average rate of change? Number 3, what are the 3 formulas that represent the average rate of change? 4, calculate the average rate of change of the function d of t equals 10t squared from t equals 5 to t equals 5 plus h when h is 0.01. As h got smaller for the function d of t equals 10t squared, what was the slope of the secant line doing? And 6, how is finding the average rate of change useful or helpful when we want an instant rate of change? These right here, we're going to be answering throughout this video, so it's important that you pay attention and take notes whenever these come up. Hey, heads up, we're going to be answering the first 3 questions right now in this next slide. The average rate of change and the secant line, what are they? So in order to go ahead and hash up this topic, we're going to take a look at a graph right here, a visual. What I graphed for you right here is the function f of x equals x squared. It's a basic parabola, intersects at 0, 0. And we want to find the average rate of change between x equals -2 and x equals 0. The first step you want to do is you go on the x-axis down here. You identify where x is -2, and then you go up to your graph until you hit the curve. Once you hit the curve, that's your y value right there. It's going to be -2, 4. Great. Now the next point they said is x equals 0. So we're going to go to 0 and we put our point there. And it's 0, 0. Make sure that you're, please draw a picture of this and graph this. You want to make sure that you have a full, complete set of notes. Okay, once you have these 2 points, right, and our goal is to find the average rate of change, what you do next is this. Draw a line between the 2 points. This line actually has a specific name. Let's write this down. The secant line. The secant line is basically a line that connects any 2 points on a function or graph. This right here, this line is connecting these 2 points on the function f of x equals x squared. Now get this. The slope of this green line right here is called the average rate of change. That's what it is, everybody. The slope of this secant line is the average rate of change. So all we got to do is find the slope of the secant line and we'll be having this average rate of change. Let me just get rid of this box here. Make sure you wrote this down. Now, to find the slope, there's various different methods. You could do it visually by doing rise over run, and you could also use 2 points and calculate the slope using the old traditional Algebra 1 method. So anyways, let's do it with the old way. So you start at 1 point and you're going to do rise over run. So this one, it looks like I have to move down to hit this point. And this is 4, and then it looks like this will be 3 because that's 2. So then that's 1, 2, 3, 4. So we went down 4 units, so that's -4. And we went over 1, 2. So down 4, that's -2. Over 2, so that's going to be divided by 2. So it looks like we have -4 divided by 2, which is going to be -2. Let's go ahead and double check our calculations by actually writing down those 2 points, right? So we got -2, 4 from this point and 0, 0 from this point. So how we do it, always label your points, right? Keeps yourself organized. We do x1, y1, x2, y2. And this is our old school formula for slope, y2 minus y1 all over x2 minus x1. Let's substitute our values, and I specifically color coded it so that the y values are in red and the x values are in blue. You want to make sure you keep those together, and y values are always on top. 0 minus 4 is -4. 0 minus -2, double negative, this is going to become positive. So what we have is -4 divided by +2, and our slope ends up being -2. So the average rate of change, or the slope of this green line right here, the secant line, is -2. Now the average rate of change basically tells us on average how the function is behaving. So notice this green line. I mean, it's not going to precisely be an exact way in how this function is behaving, because look, this function is curved, right? This line is basically kind of ignoring some of that curve and just making an approximation of how this function is behaving. For example, this function is decreasing and the slope is also decreasing. So we know some information from the average rate of change, but not everything. So it gives us a bit of that. Okay, so there are 3 different ways to actually represent the average rate of change. One of them was this old school formula. Here's another one. You again write all this down. So the next one is x1 comma f of x1. So this one comes from basically taking a point, and you take that point and you plug it into your function to get your y value. That's all this is. And then you have another point, you take that x value, plug it into your function to get your second output. This is actually the same thing. So this, right, change of y over change in x, that's rise over run, is actually equivalent to this right here. The only difference is that this right here is written in function notation, that's all. So this is the same thing. This is the second way to represent the average rate of change. There is a third way. The third way is one we're actually going to be using in this unit, and it's actually really important. It looks like this. Now don't get freaked out. We're going to be working through this one. But how this works is that we have an x, we plug it into our function, we get our output. Great. To get our second point, what we do is we move h units away from x, and we take this new input and we put it into our function, which gives us our output. Now if you want to try to visualize this, imagine right here that you have your x, but then if you want x plus h, you move h units to horizontally to the right, and then you get x plus h right here, and that's your second point. And to get the full point, you plug it into your function. That's how this one's going to work out. If we go ahead and rewrite it as change in y over change in x, we get this. But we could simplify the bottom. We have x minus x. Look at that. And then we just have this right here. This is equivalent to this, and it's equivalent to this. All of these 3 right here represents the average rate of change. All of these 3 formulas here represent the slope of the secant line, which is the average rate of change. This formula right here, though, it has a very special name. It's called the difference quotient. It's super special because we're going to be playing around with this h right here. We're going to be changing what h is, and it's going to tell us some different information. Well, okay, let's go ahead and move on from this one. Let's see if I hit all of the first three questions. So the first three was, what is a secant line? We covered that. Number 2 is, what is the average rate of change? Yep. And number 3, what are the 3 formulas that represent the average rate of change? Check, check, check. All right, let's move on to the next part. So we're moving on to make sure we answer question 4, 5, and then 6. All right, so how fast am I going? So we have a specific learning target by the end of this video, which is I can evaluate the average rate of change using smaller intervals. So we're looking at problem 7-94. We're taking a look at a function, d of t, which is equal to 10t squared feet. And it's going to be continued to be distance. So this is a previous problem. It's going to continue to be a distance function with respect to time of the car from problem 7-80. And the time, I believe, from that past problem was in seconds. And d represents distance. Again, so time is in seconds, and my d function is distance. Okay, so this represents a car traveling. We're going to go ahead and calculate the average velocity of the car from the interval t equals 5 to the interval t equals 5 plus h. And h is going to be 0.5, 0.1, and then 0.01. So what this tells me, it looks like we're going to be doing 3 calculations. But actually what's going to happen is I'm going to do the first 2 with you. And on the quiz today, you're going to be doing this last one on your own based on the notes that we took. So just make sure you take your notes here, and this is going to answer question 4 in your learning today. All right, so let's go ahead and set this up. One of the first questions that come up sometimes is, well, what is average velocity? So average velocity is change in distance over change in time. Change in distance over change in time, luckily for this problem, is the same thing as change in y over change in x, which is basically the slope and or the average rate of change, slope of the secant line. So we're actually doing the same thing that we just went over in the last slide. But to find the slope of the secant line, we need the 2 coordinate points. Okay, so 5 is going to be my first coordinate point, my first x value, think of it as my x. And my second x value is going to be 5 plus h. So to get my first coordinate point, I have to take 5 and I have to plug it into my function for t. So when t equals 5, it's going to be 5 squared. That's 25 times 10 is 250. See that? 5, 250. That's how I got my first coordinate point. You can even pause the video and go back if you want to see a repeat of that. Now notice, and I'll go ahead and talk about this one, how I get my second coordinate point for this problem. They said that the next time is going to be 5 plus h. I'm going to just repeat the process, except instead of t, I'm going to take 5 plus h and plug it in for t right here. So then I get 5 plus h squared and then the 10 on the outside as my output. So there we go. We have our 2 coordinates. And then in a second right now, we're going to go ahead and do the first one, which is when h is 0.5. Okay, so when h is 0.5, let's do some substitution, everybody. So notice that this h now became 0.5. All right. Now what we're going to do next is some arithmetic, basically some calculator work. So 5 plus 0.5 is 5.5. Then we have here 5 plus 0.5 is going to be 5.5. So what you got to do next is you do 5.5 squared, then you times 10. Remember PEMDAS, you do exponents first. When you do that math, you should get 302.5. Great. Now that we have two coordinates, we could jump into calculating the average rate of change, which is going to tell us the average velocity of the car. Change in y over change in x. Remember, the y's always go on top of the slope formula. Oh, sorry, I don't know why. You don't have to rewrite that. But when you do that calculation, you get 52.5 divided by 0.5. And we get 105 feet per second. Don't forget your unit. Remember, this was going in feet. And our time, I'm just going to tell you it's seconds, because this is from a previous problem. All right, so we're done with 0.5. Now let's do it when h is 0.1. Same setup, except now h is 0.1. So we're going to go ahead and substitute, do our math, change in y over change in x, use some calculator. And again, I really don't know why I kind of repeated this step, so you don't have to rewrite this one. So it looks like it's 10.1 divided by 0.1. And I get 101 feet per second. Notice that h right here, it's 0.5 and then it's 0.1. H is getting smaller. The average rate of change is also doing what? Looks like it's also getting smaller. So it was first 105 feet per second. Now it's 101 feet per second. I wonder if this trend is going to continue, right? So it's your job though to find out, because now for when h is 0.01, I'll help you set it up, but you're going to finish this up in today's quiz. So when h is 0.01, we're going to again have the same points. You're going to make your substitution, and then you're going to finish this up in the Google quiz. So please be prepared to work this out. Now, if there's any concerns that you have about working this one out, you want to just make sure that you show up to my virtual office hours, or your teacher's virtual office hours. All right, all your teachers will be having their virtual office hours, depending on what time they told you. So just be there if you need some support, because we all have the same quizzes in our math department that we'll be giving. All right, so great. Let's see what questions, and I'm taking a look at the notes I took here. So so this is going to be question 4, that you have to calculate the average rate of change when h is 0.01. And we kind of hit on question 5 when, as h is getting smaller, what is the slope of the secant line doing? And this right here, these are the slopes of the secant line, because remember, slope is the change in y over the change in x. So this is what the slope is doing right here. And then we're going to talk about the instant rate of change, which is question 6. Okay, so let's go ahead and visualize this though. And in order to visualize this problem, 10t squared, I'm going to use handy dandy Desmos. This is a cool tool that I'm going to go ahead and also put in the Google Classroom so you could play with it too. So 10t squared, I kind of had, in order to use this tool, I had to put it as 10x squared, but it represents the same thing, where this right here is distance and this right here will be time. Now the A for this tool basically is what point am I looking at. So let me look back at my problem. The point in question seems to be t equals 5. So that means t equals 5 seconds in this problem. So we're going to take a look at when that's 5. So see, when time is 5 seconds. And then we initially had that h was 0.5. So h 0.5. Look at that. It drew the secant line for us. So this is a secant line to tangent line function. We'll talk about what tangent line is later on. But this right here, remember guys, the line that connects 2 points is called the secant line. And take a look, it even has the 2 points that we created right here. See? So it works out. Okay. So this is cool. So basically, if we zoom in right here, so this is a car that's traveling some distance. This is my distance. This is my time in seconds. Between 5 seconds and 5.5 seconds, the car was going at 105 feet per second, right? That gave me an average velocity. But let me go ahead and talk about, well, what if I want to know how fast the car is traveling exactly at t equals 5 seconds? That means I want to know at that instant, what is my car's speed? How to help you think about this, think about when you're driving and you're looking at the speedometer in the car. What you're looking at is not your average speed, right? You're actually looking at what is your actual speed. Like if you're speeding and, a cop stops you, because you're actually speeding at that instant. What if I want to find the actual speed of the car? So let's see. Let's see if this problem helps us. So the next point was when h was 0.1. So that's, and h, by the way, y'all, sorry. So h is basically the horizontal distance from this point to this point. Think of this like a triangle. And h is the horizontal distance. And we're going to go ahead and shorten this horizontal distance. We're going to now make it 0.1. Look at this. It got closer. I have to zoom in a bit. So now the horizontal distance of this like imaginary triangle, horizontal, is 0.1. Now we're getting a better approximation of the actual speed of the car. So between t equals 5 seconds and 5.1 seconds, we had that the average speed was, and let's go back to our calculations, it was 101 feet per second. Great, it's giving us a better approximation of what is the actual speed. Now we could do even better. Like I still want to know exactly at 5 seconds, not between 5 and 5.1 seconds. So then that's when we go to 0.01. Look at this. Look at this, guys. When you put 0.01, these points are almost like virtually on top of each other, almost like they're 1 point. Wow. But of course, if we zoom in, they're 2 separate points. But these 2 separate points, so between 5 seconds and then 5.01 seconds, they're really, really close. I believe that once I calculate the average rate of change, or the slope of the secant line right here, it's going to give me a really, really, really good approximation of the instant rate of change of the car. So exactly how fast am I going at 5 seconds. So remember, it's going to be your job to calculate this on the quiz today. So let me just make sure that we finished up what we talked about. And yeah, the slope of the secant line looked like it was getting smaller and smaller each time we did our calculation. I think we hit all of our learning goals and questions here. And we did this. Yeah. All right. So again, like I mentioned, make sure that you go to the virtual office hours if you have questions of your teacher. And good luck. Make sure you take that quiz by 11:59 p.m.